I was asked to give a talk about the geology of El Cerrito, the geologic history of El Cerrito, so I'll try to do that and work it in with the anniversary, the 100th anniversary. Anybody know what anniversary it is of the rocks that are under our feet?
10,000 years.
10,000 years? No.
6 million.
Getting closer. Okay, that'll be the first question that we'll address. Next. The first thing we got to try to do is get our heads around the concept of geologic time, which is totally unlike anything in a human lifetime. So, John McPhee, the great writer, he wrote Basin and Range, among many other things, said if you consider Earth's history as a measure of the English yard, from the tip of the king's nose to his outstretched hand, just one stroke of a nail file would totally eliminate all of human history. Next. Try to think about how long it would take to accumulate a mile-thick section of sandstones, 1 grain at a time, that we see in the Grand Canyon. Next. Well, we've actually been able to date it, and it took... Go back. There. Been able to date it, and we know it took about 550 million years. And we also know that's only about 10%, 12% of Earth's history. So it's a huge, expansive time that we have to try to think about. Okay, next. So this is the geologic time scale, and it starts with the beginning of the Earth about 4.5 billion years ago. It's broken up by geologists into great sections. The period before life, or that has single-celled life, is called the Precambrian. Starting in the Cambrian, we have the Paleozoic. That's the time of trilobites and the first fishes, first reptiles and amphibians. Mesozoic is the time of the dinosaurs. And then the Cenozoic, the most recent, would be the time of mammals. And humans are just this last little bit, the last million years or so. Next. So the answer is, next. The rocks in El Cerrito range in age from 150 million to about 11.5 million years old. So the older rocks actually span about 90 million years. It's called the Franciscan Complex, or the Franciscan Terrain, Franciscan Melange. What it means is it's a group of rocks that started out in the deep ocean, were brought along with the ocean floor to the continent, taken down into the earth with the subducting or the down-plunging ocean plate, squeezed and heated up, and then thrust back by faults and such back to the surface. And I'll go into that in a little more detail in a moment.
So are they Catholic?
So if they what?
They're Franciscan, are they Catholic?
Good one. Go back. Okay, in the last one, I just want to point out the most recent is just a thin skiff of rock at the surface, at the top of the hills, like around Madeira School and such. It's a very light-colored lava flow. It's called the North Bray rhyolite. It's the same rock as Indian Rock in Berkeley, for example. Okay, next. So the Franciscan assemblage is 2 different kinds of rock. One geologists call a meta-graywacke. Just means it's metamorphic. It's been squeezed and heated. And graywacke is just an old German term for a dirty sandstone. So it's a dirty sandstone that accumulated in the deep ocean as ocean landslide deposits. So we get a bunch of sediments piling up on the continental shelf. When you get enough of them, they become unstable. Maybe there's an earthquake, something shakes them, and they go cascading down into the deep ocean. That's what a graywacke is. It's also called a turbidite, and I'll get into that in a minute. The other kind of rock is a blueschist, and that is ocean floor rock. If you think of the black lava that comes out at Hawaii, It's called a basalt. Most of the ocean floor is that black lava kind of rock. When it gets metamorphosed, it turns into blueschist. So the minerals slightly change, and we have a rock called the blueschist. And next,
How does it get metamorphosed?
by being dragged down into the earth and getting heated up and squeezed. And then this is the 11 million year old North Bray rhyolite. It's a light colored rock. There's an example of it up here. It looked kind of rust colored at the surface, but when you crack it open, it's almost white. And it's got a lot of silica in it. That's what gives it the light color. Silica is just quartz. The source is thought to be around Round Top volcano in the Sewley Volcanic Preserve in Oakland. Not sure how it got here. It might have flowed this far, but usually this kind of lava doesn't flow that far, so it may have flowed across the Hayward Fault and then been carried north that way. Next. So how did these rocks get here? Next. Yeah. So we'll talk a little bit about plate tectonics, which is a big part of the history of this area. And in order to understand plate tectonics, you have to think of the Earth. The interior of the Earth is molten or plastic, so the mantle can actually move around. But the crust of the Earth is thin and brittle. So it cracks like an eggshell would if you dropped it. And those plates on the surface, the brittle plates, actually are constantly moving around. The North American plate, for example, is separating from Europe along the mid-Atlantic rise at about 2 inches a year. And we can measure that movement. So the North American plate is moving this way now. The Pacific plate, this huge area, is moving slightly to the northwest. We are right here. Next. So there's the movement arrows of these plates. And right now we're sitting on what's called a transform margin between plates, so those plates are sliding sideways relative to each other. Next. So this is just the 3 different kinds of plate margins that we know. This is a transform, so the 2 plates are sliding sideways. This is a spreading center. That's the mid-ocean ridges where the plates are moving apart from each other. And if you go to Iceland, for example, you can actually see that. There's a big rift valley, and one side is Europe, and the other side is North America. And then this is a convergent margin, or subduction, where 2 plates are coming together. If they're 2 continental plates, you'll get mountains buckled up. That's what's going on with India and Asia, causing the Himalayas. If you have an ocean plate and a continent plate coming together, usually the ocean plate dives back into the mantle because it's heavy and dense, and continents are light and fluffy. Some geologists say that continents are granitic, they're the scum of the earth. Basically, they float up lighter. Yeah?
I was just going to add that the crust is very thin compared to the size of the earth, which is also a reason why these things can move.
Right.
It's like you were saying, like an eggshell of an egg. It's really very thin. For us standing here, it seems big.
Yeah, and the crust...
It's very thin.
The crust can be anywhere from 10 miles thick under the oceans to 40 and 50 miles thick under the continents, but still compared to the 4,400 miles to the center of the Earth is very thin. Okay, next. So, El Cerrito began out in the Pacific. This is a paleogeographic map, a reconstruction of what North America, the western part of North America, looked like. In this case, 15 million years ago, by Dr. Ron Blakey, Northern Arizona University. He's made a whole series of these maps. They're online if you want to go looking for them. But what we had at that time, which would have been in the Jurassic, we had El Cerrito out here sitting between 2 subduction zones. So the ocean was going underneath here, and this is a volcanic arc, much like the Aleutians today. And then this is another subduction zone, and we had a volcanic arc here, that is much like the Cascades today, where the Pacific plate is still going under North America, melting, and you get volcanoes at the surface. So, and the rocks were to indicate they were deposited in a deep ocean environment. Next.
Would that have been much further south?
I don't know what the latitude would have been. Yeah, it might have been, and I could look it up, but the plates are constantly moving, so it's likely it would not have been at this latitude. Okay, next. So the next slide, we're going to look at a schematic cross-section or slice through this area here. Next. Okay, so from 250 million years ago until about 25 million years ago, this was a situation going on in the East Bay Hills and the Bay Area. You had the Pacific Ocean out here. This would be the Pacific Ocean crust. It's coming toward the continent, plunging down into the mantle and melting. The sediments that are on the ocean floor are being scraped off and pushed back to the west, and that's how they get pushed back to the surface, but they're actually first dragged down with the ocean crust. We had a broken off piece of ocean crust here with the Great Valley sequence. So what you see out in the Great Valley is pretty much flat lying, totally undeformed rock until you get to the west side, and then it's been pushed up and it's near vertical.
So the horizontal line is like the San Joaquin Valley?
This here.
Okay, good,
Yeah,
good.
yeah. And then at the surface, beneath this great big blob of magma that has cooled and now is the Sierra Nevada, we had volcanoes. Oregon and Washington, we still have that situation. It's called the Cascades. You go down 5 miles below the Cascades, you've got all granite. You bring that to the surface and erode it, you got another Sierra Nevada. So that's what the Cascades is what we looked like prior to 25 million years ago. Okay, next. So we would be in this position here. Next. So metamorphic rocks tell you what they underwent in a couple of different ways. You look at their texture and you can look at their composition, and that tells you what they've gone through and a little bit about what they started as. So as you get increasing amounts of compression, first you get slaty cleavage, then you get schistosity, which is aligned minerals like micas and stuff. They're platy minerals. They all line up the same way. And eventually you get compositional banding like this, where the minerals don't melt, but they start to migrate. So all the quartz goes together and all the dark minerals like hornblende goes together, and you get a nice Gneiss, another old German word, but it basically means compositionally banded rock.
Is this from heat or heat and pressure, or just get it
Both,
just from
but
pressure?
mostly pressure
Most pressure.
for this kind of mineral alignment.
Okay.
You can also have metamorphism with just heat.
Mm-hmm.
That's how you turn a limestone into a marble, for example. You recrystallize the rock.
But this is pressure. Mostly.
Right, this is what I'm trying to address right here, is just the pressure part of it. Yeah.
Are these differences from when the rocks start to be pushed upward?
These
So
are,
that when they start to be pushed upwards, it's on the left, and then the same rock, as it goes higher, becomes
Yes.
the central thing?
yes,
And then that same rock, when it goes still higher, becomes that thing?
that's correct. Yeah, the rock actually goes through an evolution depending on how much pressure and heat it's been exposed to.
The pressure comes from the top or from the bottom?
It comes from being buried deep in the earth. If we go to the next slide, I'll show you some of the compositional things that tell us as well. Next. Okay, so these are the different kinds of metamorphic rocks. Where East Bay Hills is what's called Blueschist. The composition of Blueschist, glaucophane is the mineral that gives it that color. And by putting things like sandstone or shale into a pressure bomb and then increasing the pressure in a lab, you can actually see how the minerals in the original rock change into new minerals. And Blueschist specifically tells us that these things have been buried between 9 and 18 miles in the earth and at temperatures between 390 and 930 degrees. So that's the range of pressure and temperature that forms a blue schist. Then it had to get to the surface. Next.
But before you do that,
Yep.
1 kilobar is how many pounds per square inch about?
I don't remember that number.
Okay, but it's a pretty big number, like 1,000 or something?
Yeah, it's 1,000 bars, and a bar is like 1 atmosphere.
Which is what, 13 psi, I think,
I
right?
think so.
It's 14.5.
There you go.
So it's 14,000 psi, is that correct then?
1,400.
Okay. Okay, very good.
Okay? So, as we saw earlier in the schematic diagram, when these things are buried, the squeeze comes on, and they get pushed back up. And so the East Bay Hills that we're seeing now, this would be the equivalent position of, say, the recycling center quarry. It's right between a couple of thrust faults. A thrust fault is just one that takes old, deep rocks and pushes them up over younger rocks. So that's what was going on that actually formed these hills. First, the rocks were buried and metamorphosed. Then they were brought back to the surface. Next.
So the push is from the east in this example.
Both the east and the west
Okay.
coming together. Yes.
But the east one
It's
is
because
going up.
the Pacific plate was pushing this way and North American plate's pushing this way, and they get squeezed, the rocks in between. Yep. Okay. So here's a couple of examples of outcrops of the Meta Greywacke, the dirty sandstone. This is just off Potrero. This is just off Schmidt Lane. Next. So you can actually see bedding in there that's still the original layers of rock in there. Next. And if you look at it in detail, you can still see sand grains in there in some cases. Next. This is what a modern turbidite or greywacke looks like. It's alternating layers of coarse rock, coarse grain, going up to fine grain. That would be one package that's slumped down the slope.
Water.
And then the next one would be, again, coarse grain to fine grain, because the coarse settles out first, and then the mud and the fine sediment settles out later. And you get one on top of the other, on top of the other.
That develops underwater.
Underwater,
It's
exactly. This would be a diagram showing what happens. You get this big slug of sand and mud all rolling down the slope as an underwater landslide, and then it forms these little lens-shaped deposits at the base of the slope. Next. And then this is the original ocean floor basalt or lava that has, in this case, compositional banding, so it's almost a gneiss. This is just above the recycling center, and this is a really blue-green rock that you could see at Chevelin and Moser, just under the power lines. This is a beautiful example of the Blueschist. Next. This is how it actually formed. This is an example of the lavas coming out under the ocean right now, southwest of Samoa. They form these pillows that are about 1 meter across. This is pillow lavas off Hawaii. When lava erupts under the ocean, it forms these little blobs that cool, and then it breaks through and it forms another blob. And geologists call them pillows. Next. If you go out to Point Bonita Lighthouse on Marin Headlands, you can see these pillows very well exposed right there by the lighthouse. Next. So, those are the rocks that became the Blueschist. And it started out here at or very close to the spreading center in the Pacific Ocean and gradually migrated toward the edge of the continent. This is another paleogeography map done by Dr. Scotese at UT Arlington, University of Texas, showing late Cretaceous time, about 94 million years ago. Next. And at 80 million years, again, this is another map by Ron Blakey, and now we're closer to the coast. And this is what North America looked like, actually the west half of North America, because there was a big seaway that flooded from the Gulf of Mexico up to the Arctic during the Cretaceous. And you have an eastern North America and a western North America. Next. So this is kind of a sequence showing what happened to the Pacific Plate, and on the east side of the spreading center was called the Farallon Plate, named after the islands. About 25 to 30 million years ago, that spreading center connected with North America. And where it connected, you got this sideways motion, the beginning of the San Andreas system. And here's the situation where we are now, where the San Andreas goes from this remnant of the Farallon Plate. It's called Juan de Fuca, and it's offshore Oregon and Washington. That's what's causing the Cascades to be volcanoes now. And it goes all the way down to the Gulf of California, where again it becomes the East Pacific Rise. And here you have a remnant called the Cocos Plate, and it causes all the volcanoes in Central America, where it's going down underneath. So, but in between, you've got now the San Andreas system, which is the situation as it is now. Next.
Before you do that, can I have a question, please?
Okay.
That little slide, so what you're saying is that north of us, the plates are going underneath each other.
Yes.
South of us are going underneath. And we're in a region where, what, because we're just getting dragged sideways? Is that what's happening in that middle image?
Right. The North America is going this way.
Okay.
The Pacific is going this way. But in between, you've got spreading going away from here this way.
Okay.
So relatively to each other, one is going this way and the other is going that way.
Okay. Okay.
Gary, I read somewhere that I think that one particular plate is moving north. And so that's like one reason why we're moving sideways. You know, it's moving north, so there's a portion, that's why we're not totally going, the oceanic plate isn't totally going under the continental plate. But that other plate just north of us, I think, under that last slide we had on the right, it's moving north, so it causes this strike slip movement.
Yeah, the Juan de Fuca Plate is still going underneath the continent. Where we are, the Pacific Plate, because the mid-ocean rise now is underneath North America. It's gone down underneath the continent. So we're actually at the edge of the Pacific Plate, which is moving to the north and west. And the North American Plate is going like almost due west. And relative to each other, you've got one side going northwest and the other side going southeast. As you can see here. So once you get north of this, about Point Mendocino, you've got the Juan de Fuca Plate, and it's still going under the continent.
Excuse me, can you move? Very good, thanks.
Yeah. So this is still going under the continent, north of Cape Mendocino, but between Cape Mendocino and the Gulf of California, you have this relative motion going on.
Is that the plate that affects Seattle?
Juan de Fuca Plate is the one that's causing the Cascadia fault zone that's just offshore and that everybody's talking about, might jump and cause tsunamis and things like that. Yes. And then north of Seattle, you've got an equivalent to the San Andreas called the Queen Charlotte Fault, which is also a lateral fault. That's why you stop having volcanoes, but you've got lots of earthquakes, and it goes up to the Aleutian Trench and curves around, and then you've got subduction again and all of the Aleutian volcanoes. So yeah, you've got a bunch of things going on.
Very active.
Yes. Okay, so let's talk about the Hayward Fault, which is probably near and dear to a lot of you because we live real close to it. The Hayward Fault is a right lateral strike slip fault. That's what geologists call it. What that means is they're moving sideways, one side relative to the other, not up and down that much, but mostly sideways. And as you look across the fault, the other side's moving to the right. That's what they mean by right lateral. And then strike slip just means it's going sideways. So it's part of the San Andreas system. We know that the contact between North America and the Pacific is not one break. It's a whole series of faults. Offshore, you have the San Gregorio Fault. On the San Francisco Peninsula, you got the San Andreas Fault that the whole system is named after. Here, we have the Hayward Fault. And you have other faults going across the Great Valley until about the east side of the Sierras, where most of the fault displacement is vertical, but only a little bit of right lateral movement. So it's a whole system. It crosses the entire state. But the Hayward is one of the active faults in that system. What do we know about it? The El Cerrito strand is creeping. That means it's slipping gradually, about 1.5 inches every 10 years. We can actually measure it against human-made landmarks. The last big rupture here was around 1705. We had a geology, El Cerrito Trail Trekkers had a geology hike related to the Hayward Fault last spring. Dave Schwartz of the U.S. Geological Survey went along, and he told us that the Geological Survey trenched across the Hayward Fault in Mira Vista Golf Course. They found a forest fire ash that they were able to date crossing the fault, and they dated the last big movement about 300 years ago.
How big is the El Cerrito strand? Like, is it 5 miles, 50 miles?
The El Cerrito,
Hard to imagine what it
it
looks like.
starts north of San Pablo Bay, where it's called a different fault, and it goes south of Hayward. So it's 30, 40 miles long.
Yeah, but how wide?
How wide?
If it's a strand,
Yes.
like a noodle.
It also is not a single break in most places. It's been variously mapped at up to 1/2 mile wide.
Oh, so it's not that wide.
Well, it depends if you're living near it. I guess.
Everything's relative.
Yeah, it's all relative. Total offset on this creeping section of the fault is about 3 miles in 12 million years. Next.
Is that big or little?
It comes out to like 1/10 of an inch a year. But I suspect that, like we saw in that trench, every couple of 100 years, it can jump still. So it's probably creeping most of the time, and that's good, because you want gradual release of pressure rather than the buildup and jumping, which causes the big earthquakes. Okay, the youngest rock in the area, North Bray rhyolite, 11.5 million years old. These are some outcrops on Julian Drive, just below Madera School. Next. In detail, it's very light-colored, fine-grained lava. Next. I got this from an article that was written. It's called Stories in Stone at Sibley Preserve, 2005, by Gordy Slack. He writes, 10 million years ago, 3-toed horses and long-necked camels roamed the area, and you could still see volcanoes in the Sierra Nevada. So this is an artist's concept of what it might have looked like out at Round Trop. Next. At that time, we are now on the edge of North America. There was an arm of the sea that came in through the Bay Area. There was another arm of the sea that still existed in the Central Valley. But we looked pretty much like we do today, with a few minor details. Next. Okay, jumping to just the last million years. This would be the time of the ice ages. 1 million years ago, San Francisco Bay was a flat plain, this area, between the Coast Ranges and the East Bay Hills. By 500,000 years ago, we had a river that had cut a canyon from Carquinez Strait through the Golden Gate, which was exposed, I guess, at the time, and then out to the coast. Next. So, 20,000 years ago, we were at the height of the last ice age. Sea level, because there's so much of the Earth's water was tied up in ice sheets, sea level was 400 feet lower. The coastline was 25 miles west of where it is today. The Farallon Islands were mountains on the continent. And the river that drained the Central Valley had cut this canyon all the way through to the coast. The end of the Ice Age happened between 12 and 15,000 years ago. So that's the time frame that you were thinking earlier. Glaciers began to melt, sea level began to rise. It's still going on. Sediment carried by the Sacramento River got deposited and started to backfill this canyon. And eventually the Pacific spilled through the gap at the Golden Gate and began filling the bay.
Quick question. When did humans start walking around? How many?
About 12 to 15,000 years ago is when we think, when we have the first evidence that the Native Americans made it across the Bering Strait.
So the shoreline is pretty different, huh?
Yeah.
Okay.
And in fact, in a lot of places, not just here, but in offshore Europe, in the English Channel, which had been dry, off the East Coast, the fishermen have dredged not only human artifacts, but like mastodon bones from 200 miles offshore, off the east coast of the U.S. and in the English Channel. A lot of stuff has now been drowned. Yep. Next. Okay. That kind of concludes the historical part of the talk. Now let's talk about other things that might be of interest, like earthquakes and tsunamis and landslides. Next. Next. So, the thrust faults are dead, but the Hayward Fault is definitely alive. The first recorded quake in human time, European time, that we've been here was in 1868 at Hayward. It's estimated to have been a 6.8 to 7.0 magnitude earthquake. The maximum offset on the ground was 3 feet laterally, and it was up slightly to the east. In fact, there were 3 quakes that had a magnitude 6 to 7 that were recorded during the 1800s. This is a Google Earth view looking north. This is Moser. Hillside nature areas here. The Mira Vista Golf Course, I believe, is here. Yeah, and this is Arlington Park. So the fault, you can see the west side is moving relatively to the north, and it follows Arlington for a long part of its stretch. Next. The Geological Survey, the USGS, has a Did You Feel It map. This is online, and they encourage people to respond if you felt an earthquake. You can log in and put in your observations. This is the Did You Feel It map from the El Cerrito earthquake. I guess it was under Kensington last June 21st. It was a 3.0 quake. Most responders felt just a slight bump. Next.
There was the one in Berkeley that was 4.4. Oh, this one here.
There it is. This is the one that happened a week and a half ago. In the middle of the night, 2:40, if I'm not mistaken. It was a 4.4. Most people who felt it, who woke up, felt real shaking going on. Next. Okay. Back in 2012, the Geological Survey did a study where they estimated there's a 1 in 3 chance of a 6.7 or greater earthquake along the Hayward Fault, which is this one here. You can see its extent, in the next 30 years. So they're pretty confident it's going to jump, have a good-sized earthquake. A magnitude 6 to 7 is easily felt. Your chimney will topple over if it's not braced. Your furniture is going to move. There'll be substantial damage to big buildings. We know that the Loma Prieta quake, we had a freeway collapse. Hopefully that won't be happening. But that was a 6.9.
How do they determine the 30%?
I'm not sure how they do that. They must look at statistical...
It seems kind of strange to me.
There's a distribution of earthquakes that basically is logarithmic. So you have lots of small ones and very few big ones. So if you can make the historical curve of lots of small ones to few big ones and figure out the time frame for those, you can probably make a prediction. I'm guessing that's how they did it.
Or is there a possibility too that they're actually feeling the pressure build? I mean, aren't they measuring them constantly for the
They're trying to,
movement
yes.
and pressure and that?
There's experiments going on now to measure the pressure buildup in the earth. Stanford University is leading an effort where they've actually drilled a well through the San Andreas out in the Central Valley, and they're trying to measure with strain meters and stuff how much pressure builds and then see what happens. But this is not an exact science right now. It's probably more or as much an art as a science. Yes?
Why don't the geologists think it's likely that there will be a succession of small earthquakes rather than one big one, like a lot of 4.4s?
Why don't they think there will be a lot of small ones? You know, I'm not sure. This was specific to the Hayward Fault. It was probably somewhat generalized. We know that certain sections of the Hayward Fault do have big earthquakes, like the ones in the 1800s down by Hayward. But the strand up here appears to be slipping slowly. So you get a bunch of smaller ones like we've seen with the Did You Feel It maps of 4s and 4.4s and things like that. And I'm hoping that's what continues to happen, because I live about 100 yards away from the Hayward Fault, and I don't want a big one.
I also get the impression, I did some science writing, so I got a tiny, I'm no expert, but that there's also just a historical record. Like, I think Hollister, they have hundreds of earthquakes a year.
That's all you can go by is
And
historical
they're tiny
record.
ones. And so that's sort of part of the geology there. And in other places, they just tend to have more small ones. Or
Yep.
and
That's where you get that curve I was talking about.
Yeah.
You're measuring lots of small ones and fewer bigger ones and very few really big ones. Yeah. Yes.
I understand that some configuration of different kind of faults can set a certain maximum, the strength of earthquake possible on them. Is there a maximum for Hayward Fault?
I don't know, to be honest. I'm not a seismologist. But probably, if you know these sorts of things, you can figure out what might be the largest size. But all I've heard people talk about is 6 to 7 magnitude.
So if I may speak to that, I might know a little bit more than some of the people in the room. It has to do with how long that fault can rupture. In other words, the longer that it can rupture, the bigger the magnitude. So when we look at some of these strands, they have a certain length. And so the seismologist will say, it looks like this could rupture over 15 or 20 or 30 miles. And then they can correlate that with duration of shaking, how violently and how long it's going to shake, and come up with a magnitude. That's roughly how they do it. With regard to these probabilities, the way I understand it is they look at as this gentleman was saying, that we know that the plates are kind of moving so many inches per year. And we know certain parts, because we can measure with the very precise satellites and stuff, are kind of locked up. They're not moving. So the seismologist is going to say that the pressure is building. It's building. And if all that pressure is released at one time, that's like a big earthquake. If the pressure is getting released by these little earthquakes, it's moving, it's slipping. And the area down around Hayward, the city of Hayward, is notorious. It seems to be sliding there quite a bit. And people that give you earthquake talks can go out and point to curves and stuff and show where it's
That's the next slide.
So
Yeah.
that means,
But up here,
that means we're safe because we're slipping all the time.
that would be, I believe that's the case, that if that happens. But if you talk with the seismologist, I'll tell you that the difference between a 5 and a 6 earthquake, the amount of energy released is enormous. It's not a linear thing. So even if you need a whole lot of small ones. You need 1,000 small ones to make up for the energy to alleviate a 6. You see that? That's what's deceptive about this. You follow me? We think between a 6 and a 7, yeah, it's only a little bit of a difference. But energy-wise, it's a huge difference. So you'd have to have, 4.4s every day or something to be dissipating that energy. Do you see that?
So in Hollister, they'll never have a big one. In Hollister.
Why is that? What's
Because they're having so many.
I was just wondering, like, for instance, if the depth, they measure a lot of the depths for the earthquakes, or shallow ones, safer, or we have to worry about the deeper ones?
Generally speaking, a deeper earthquake is going to be felt less violently at the surface. It's the shallow ones that have the most jarring effect at the surface. In general. There's no guarantees. The Earth does what it wants to do.
It would seem to be one way to interpret this business about a lot of earthquakes and going all this is sort of how slippery the fault is. I imagine that. And if it's not very slippery, then it's going to make
Right.
big jump.
But I don't know how you measure how slippery an Earth.
I don't know how to make that technological.
Okay, so how do we recognize faults? Generally speaking, we look for scarps, breaks in topography. We look for linear valleys, offset streams, or streets, or fences, aligned springs. So groundwater likes to flow through the broken rock in a fault zone. And this indicates how it's usually not a single break, as I mentioned before. It's usually a fault is going to be a zone, a braided zone of breaks in the rock that, in case of Hayward Fault, can be up to half a mile wide. Next. Okay, another Google Earth view looking north from the Berkeley Stadium to Richmond. The facade of Berkeley Stadium, you can actually see a 2-inch offset on that. When they were doing the remodel of it, they actually left that because the Hayward Fault goes right through the stadium. On Olive Avenue in East Richmond Heights, you can see a curve offset, 2 inches on either side of the street. In a lot of places, you don't see that kind of offset because we paved over it or landscaped. But in a few places, you can actually see these things. Yeah.
I was going to talk about the stadium. I thought it was too off key. College football just ended. But are you meaning to say all through the stadium, there's nothing that connects it from the west side to the east side? There's no mechanisms that cross the fault line, or? I mean, I wouldn't want any piece of cement to cross the fault line. So I realized, how do you put a $300 million stadium right dead center on the fault line? That seems construction nightmare to me.
Yeah, but they've done it. Go ahead.
Yeah, keep in mind, the city was built in about 1930. I mean, they didn't know it at that time.
But it's been rebuilt.
No, it hasn't been rebuilt. It's been seismically upgraded, and they allow for relative movement. In other words, this joint is. In other words, there's certain areas that are like on blocks. So when it slides, when the fault, if it moves 6 feet or whatever during the big one, it won't crumble. Certain segments of the thing, like bricks, like bricks. You see, they'll be dislodged, but they won't come tumbling down. That's kind of the rationale.
Go ahead.
Actually, why $400 million for the stadium was they actually installed rubber baby buggy bumpers in between sections.
That made me feel good.
Good.
Yeah.
All right. Next.
Has anybody seen the one over in Point Reyes from the San Francisco where it moved like 15 feet? And
Yes.
they still have that
The fence that's been offset.
Yeah, it's amazing thing to see.
So I have a general theory. So my theory as an MC, that when the first person gets up and leaves the lecture, it means that we're asking too many questions. So let's try to
Okay.
get the question.
All right. Just a few more now. This is an online geologic map of the Oakland Quadrangle, of which El Cerrito is a part. If you're interested in geologic maps, you can find this online. I've tried to highlight where the Hayward Fault goes through here. Mostly it's along Arlington. We would be right here right about now. Next. So what this shows is things like faults. It shows where you've got rock, which are usually the bright colored units, these things. It shows where there's soil, which is the yellows. And the yellows are broken up into other things like landslides, which would be of interest to a lot of people. There's a big landslide, for example, on both sides of Moser. Next. This would be the golf course, Mira Vista. Next. And that shows where the Hayward Fault goes through it. Next. Okay, liquefaction is an item of interest, but in our area, it's not that big a deal. The Mission District, Loma Prieta quake, it was built on landfill, buildings subsided. Here, we've got the high range of concern is really just along the coast. And then the flats, they say there's moderate concern. I'm not sure that it would be that big a deal unless the soil is waterlogged. Next. Okay, El Cerrito commissioned a hazards map a few years ago. What it shows is the Hayward Fault zone, landslides in red, the area of high fire danger outlined in green, and one small area of flood concern.
Can you identify some streets?
Yeah, where are we at now?
Yeah, where are we at?
This would be, I believe this is the Moser landslide. So we would be right in here somewhere. Maybe down here.
Okay.
Yeah, this is San Pablo. Next.
Is that online? Does our city have this one?
Yes, that's online as well.
You know, one thing I'm planning to ask Gary is whether it would be okay for the Historical Society to put this whole presentation online.
Sure.
So I think we'll probably do that, so you can always check it out on the Historical website.
Recognizing landslides, a couple of things. You've got scarps at the head, sometimes multiple scarps. This scoop-shaped form, both in map view and in cross-section. And then you've got this jumble of rock at the toe. So the next slide will show an example. On Havens Place, one of you had mentioned that you had a landslide near Potrero last spring because of all the rain. Here's a little landslide off of Havens Place. This is a detail showing a couple of scarps and then the jumble of rock down at the toe. Yeah.
What do you know about the lake mouth slide?
Nothing. Where is that?
It's in Kensington.
It starts off with the lake County, it comes down toward us.
All the way down to the high school.
I don't know anything about it specifically. I just know anytime you've got a slope and it's not got rock under it, you have potential for sliding.
Well, we're told it's serpentine kind of bedrock with unconsolidated slide debris and clay on top of it.
That could very well
It
be.
seems to be a dry slide.
Okay.
When it
And
gets
the
wet, it
realtors,
moves,
the realtors know about it.
Okay. So this is some of the things you might look for in your neighborhood. Trees that have been bent down slope. In this case, it's moving slow enough. This is just gravity driven. It's moving slow enough that the trees have had a chance to adjust and grow upright again. Cracked foundations are very common. You see those all over. Little dips in the pavement, usually on the downslope side. That's a kind of cause for concern, especially if you live on the downslope side. Next. Okay, end with tsunamis. This is an article from the Mercury News a few years ago. There's a tsunami threat. Well, not really in the East Bay. If you live on the coast, yeah, possibly. But there have been 71 tsunamis recorded since 1854 in the bay. Wave height is the most important factor in risk, and wave height is a function of the size of the earthquake. Next. Stephen Ward, a professor at UC Santa Cruz, has done a bunch of simulations. And he's taken a standing wave, or initial wave, 16 feet high, which is much larger than historical records, but still possible. And what he's done is he's seen what happens if these start in the Pacific and then impact the Golden Gate. Next. And what he's found is that the original waves pile up as they try to squeeze through the Golden Gate. The waves almost double in height to about 30 feet, which is still way less than the 220 feet high span. But once they get into the bay, they start to fan out, and the amplitude goes down. So that by the time they reach the other side of the bay, they're about 3 foot high. So, I mean, you can still do a little bit of damage with a 3-foot wave, but it's not, oh my God, it's not Fukushima, right? That was a 30-foot high tsunami. Bottom line is, I wouldn't worry too much in the East Bay about tsunamis. Next. That's it.
I was curious about the rock because I heard that in the southern end of El Cerrito you have, is it granite rock? I forget. And then under our house it's serpentine. And at some point you can be able to see the difference in the rock just by looking at it. Can you talk about that?
As far as I know, there's no granite in El Cerrito.
Well, then
There would
what's
be-
the other kind of rock?
Well, it's going to be either this gray, wacky, dirty sandstone,
Okay.
or the Blueschist, which can grade into serpentine. I've got a couple of examples of the Blueschist and serpentine sitting on the table up here.
Yeah, because you hadn't said anything about serpentine earlier.
Right. That's because I haven't found any, but I've been told by some of the people in here that they have found, when they were kids, they went out looking and they found actual serpentine in the hills. So it's possible, yeah.
I've got them being lost in my yard.
Okay.
I dug hole, the hole in the serpentine to plant a tree, but I thought it was really hard.
Yeah, well, serpentine is, it's the same as Blueschist, but it's been hydrated. The minerals have got water in them, so it's on its way to becoming clay. And, yeah, they're all related. Did you?
Go ahead.
Go ahead.
Go ahead. What was it about El Cerrito rocks in the very early days that made it attractive as a site for quarry?
I think it's the fact that the rocks were exposed, easily accessible, because they were quarrying the rock for road foundations and building foundations. They were getting gravel.
Okay.
And along the edge of the bay, they wanted nice flat areas to build on, so they laid down gravel as building foundations and whatnot. The railroad needed gravel for the roadbed. That's what they were quarrying for.
There was even a rock company up in Sonoma County called Valley of the Moon that had an office here in El Cerrito.
I did a little bit of reading at some point, and there was like 3 or 4 quarries here. Not just the one by Recycling Center, but there was one up in the hills by... Yeah.
But the thing that was interesting about Valley of the Moon was they were shipping decorative rock over here. Like you put on stone to your house, and the rock that they had here that they were pouring was, as you say, just gravel. It was strictly utilitarian. You'd never use it for decorative purposes.
Okay. Yeah.
A couple of things. One of them is the working group 1999 from USGS. Back in 1999, predicted that there was a 70% chance of a 6.7 by 2030. And of course, they revise those every few years because what they're saying is be prepared. And the other thing is the difference between 6 and 7 isn't very much linearly, but logarithmically.
Yeah. And it's a logarithmic scale. Yeah.
Very noticeable. And does anybody here participate in the Quake Catcher Network?
What is that?
Okay, the Quake Catcher Network is something that Stanford and Berkeley are working on. And I have a piezoelectric device on my floor, mounted securely to the floor, and plugged into my computer. And they are monitoring my house.
So your house
and
becomes a seismograph.
Up and down the East Bay, they have people that are willing to do that. And if I stomp on the floor, I can see it change. And they don't really care about that. All they care about is if everybody in the area changes. But if you want to get involved in that, it's Quake Catcher Network, and the Earth Team at Stanford are doing it. And you can add your voice.
Great.
Am I correct in understanding that the 1 point difference is a 10 times?
Yeah, it's logarithmic. Yeah. Yes, sir.
How did Albany
Albany Hill.
How did Albany Hill get there?
I wondered that. Because it sticks out. And I suspect it's the source of the name El Cerrito, the little hill. The geologic maps don't show it as being faulted. They just show it as being resistant, more resistant rock. So harder rock. I've looked at some of the rock outcrops behind the apartment buildings there, and it looks like the gray wacky. It looks like just hard sandstone, but it might be that it's caught in a fault sliver of some kind and just wedged up. But the geologic maps don't show any faults there. So I've wondered about that. I'm not sure.
I would like to suggest that we have two more questions. Okay. That we break up into. I mean, people are leaving. You gotta think of the people who are leaving. Every person who gets up and leaves, there's 5 more squirming. This has been proven in 5 seconds. There are 5 more squirming in their seats. So I like to say 2 more questions, and then we can break up into. And Tom Panis.
Albany Hill, the same rock as Point Richmond, the same rock as Cunningham, and it looks like they're all lined up. So I don't know exactly what that means, but it's really, there's something going on there. Some geologist knows what's going on there.
And it's the same rock as Coyote Hills, I think, too. There's a whole line of them.
Yes, they
Yeah.
Something to do with people from outer space.
It's a north-south.
You got it.
Yeah.
Could you clarify where you got your landslide map from, at El Cerrito? You had a map showing landslides from
The hazards map.
Is that under the city of El Cerrito?
I believe you
Under
can go
maps.
look for hazards map in the city of El Cerrito, and you can find it online. Yep.
Okay, well, let's hear it again for